Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the vast emptiness between stars, where signals whisper across impossible distances and worlds drift without suns. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Deep in the Atacama Desert, where the air holds almost no moisture and the nights stretch clear and cold above the world's highest plateau, radio dishes turn their faces towards space with the patience of ancient monuments. The Atacama Large Millimeter Array spreads across this desolate landscape like a field of metallic flowers, each dish precisely calibrated to catch the faintest electromagnetic whispers from the cosmos. Here, at an altitude where oxygen grows thin and the atmosphere barely filters the universe's constant chatter, 66 antennas work in perfect synchronization, creating a synthetic eye larger than any single telescope could achieve. The desert itself seems designed for this purpose. Rainfall measures less than 15 millimeters per year, creating conditions so dry that mummified grass from the last ice age still lies preserved on the plateau's surface. Water vapor, the enemy of radio astronomy, exists here in concentrations so low that the atmosphere becomes nearly transparent to the electromagnetic spectrum. Indigenous peoples once called this place the Puna de Atacama, the high grassland of silence, never knowing how perfectly their name would suit humanity's quest to listen to the universe's deepest secrets. Tonight, as every night for years, computers process terabytes of data streaming down from the receivers, searching for patterns that don't belong to the familiar symphony of cosmic background radiation. The Milky Way's own emissions create a constant hum, punctuated by the sharp crackle of lightning on Jupiter and the gentle sighs of hydrogen clouds condensing in distant stellar nurseries. Radio astronomers know this soundscape by heart, can distinguish between the electromagnetic signatures of quasar jets and the death throes of colliding neutron stars as easily as a musician identifies instruments in an orchestra. The signal appears first as a gentle anomaly in the data stream, a repeating burst that pulses every 1635 days with mechanical precision that seems almost deliberate, unlike the chaotic flares of distant quasars or the lighthouse sweeps of pulsars. This pattern carries something different, something that makes the night shift astronomers lean closer to their monitors and double-check their calibrations with the methodical care of people who know that the universe delights in surprising those who think they understand its rules. Each burst lasts exactly 2.347 seconds. No more, no less, with a consistency that makes atomic clocks seem imprecise by comparison. The signal strength varies slightly, sometimes strong enough to trigger automatic alerts that wake astronomers in laboratories across 3 continents, sometimes barely distinguishable from background noise, but the timing never wavers by more than a few microseconds. Whatever generates these emissions maintains its rhythm across millions of years of travel through intergalactic space, where temperature hovers 2.7 degrees above absolute zero, and matter exists in densities so low that a single hydrogen atom might drift for millennia without encountering another particle. The frequency itself tells a story. At 142 GHz, the signal occurs precisely at the hydrogen line, the natural emission frequency of the universe's most abundant element. This cannot be coincidence. Hydrogen atoms throughout the cosmos emit radiation at this exact frequency when their electrons flip spin states, creating a background hum that radio telescopes detect from every direction in space. For an artificial signal to broadcast at this frequency suggests either remarkable coincidence or deliberate choice, as if the source intentionally selected the one frequency that would be universally recognized by any civilization capable of radio astronomy. Astronomers call these mysteries fast radio bursts when they flash once and disappear forever into cosmic silence. But this signal returns again and again, patient as geological time and twice as mysterious. Most fast radio bursts originate from within our own galaxy or its nearest neighbors. Brief flickers of energy from magnetar starquakes or neutron star collisions. But this repeating pattern comes from much farther away beyond the local group of galaxies, beyond the Virgo supercluster, from regions of space so remote that light from the cosmic microwave background has barely had time to cool since the universe's birth. The origin lies somewhere in what astronomers politely call the cosmic web's filamentary structure, the vast scaffolding of dark matter that connects galaxy clusters across billions of light years. Here, in the spaces between the spaces, where galaxies become isolated islands separated by voids larger than human imagination can comfortably grasp. Something maintains a radio beacon with persistence that defies explanation. Only the most sensitive instruments can detect it, filtering the signal from the constant background hiss of the universe, cooling since its birth 14 billion years ago. The mathematics alone suggests something extraordinary beyond conventional astrophysics. Radio waves at this frequency and intensity require energies equivalent to converting several Earth masses directly into electromagnetic radiation, more power than our Sun produces in an entire year, released in precise bursts across a transmission that spans longer than multicellular life has existed on Earth. Yet the pattern shows no signs of decay or deterioration, no indication that its source grows weaker with age or distance. Whatever mechanism creates these emissions operates with efficiency that borders on the thermodynamically impossible, converting energy into radio waves with almost perfect consistency across cosmic time. In the control room, where coffee grows cold in forgotten cups, and astronomers speak in whispers that won't disturb the delicate instruments. Monitors display cascading waterfalls of data. Each pixel represents a fraction of electromagnetic spectrum captured across millions of light-years of space, transformed into colours and patterns that reveal the universe's hidden architecture. The repeating burst appears as a vertical line, straight and consistent, defying easy explanation among the chaotic swirls and spirals that characterize most cosmic phenomena. Solar flares create more violent patterns, spreading across multiple frequencies in unpredictable bursts that follow the 11-year cycle of magnetic pole reversals. Stellar explosions bloom once and fade, leaving only expanding shells of cooling gas that will glow faintly for thousands of years before dissolving into the interstellar medium. Even the most exotic neutron stars wobble slightly in their rotation, creating subtle variations in their emissions that astronomers use to map their magnetic fields and measure their distances through parallax observations. But this signal maintains its rhythm with clockwork regularity that would impress the makers of the most precise chronometers. The Zorse appears too massive and stable to be any known type of star, too organized and persistent to be natural in any sense that current physics can explain, yet too distant and powerful to be artificial in any way humans understand technology. The pattern resembles nothing in the catalogues of known cosmic phenomena, yet it carries the unmistakable signature of reality too complex to be instrument error, too persistent to be coincidence, too distant to be terrestrial interference, too regular to be random chance. Something out there in the darkness between galaxies keeps perfect time across eons, broadcasting into the void with inexplicable determination. Each pulse carries information encoded in its precise timing, its frequency stability, its polarization patterns that rotate through space in ways that suggest the signal passes through magnetic fields of unimaginable strength and complexity. The signal travels at light speed, of course, meaning the bursts detected tonight began their journey when the Milky Way occupied a slightly different position in its rotation around the local galactic cluster. Stellar motions have carried our solar system thousands of kilometers from where it was when these particular radio waves began their journey across the cosmic dark. The mathematics of this wandering fascinate astronomers who spend their careers calculating trajectories through space and time objects that follow no predictable elliptical paths, no comfortable orbits around gravitational anchors, but instead drift through the galaxy like leaves on an invisible wind. Orbital mechanics, that most precise of sciences, breaks down when applied to objects unbound by gravity's gentle chains. Every first-year astronomy student learns Kepler's laws, the elegant equations that describe how planets sweep equal areas in equal times around their parent stars, how orbital periods relate to distance in perfect mathematical harmony. But these laws assume gravitational binding, the persistent tug of a massive body that keeps smaller objects dancing in predictable patterns around a common center. Rogue objects, planets ejected from their birth systems, asteroids flung into interstellar space by close encounters with gas giants, comets perturbed from stable orbits by passing stars follow hyperbolic trajectories that lead nowhere and everywhere simultaneously. Their paths through space describe mathematical curves that approach straight lines as they escape the gravitational influence of any star, achieving what physicists call escape velocity, with margins so large that no force in the galaxy can recapture them. Computer simulations model these wandering paths with Monte Carlo techniques, running millions of possible trajectories to map the probability clouds where such objects might travel. The calculations reveal how chaotic three-body interactions can transform circular orbits into parabolic escapes within a few thousand years. A planet orbiting peacefully around a binary star system for millions of years can find itself suddenly accelerated beyond recovery when a third star passes too close, its gravitational field creating resonances that amplify small perturbations into catastrophic instabilities. The nearest known rogue planet, designated WISE 0855 or 7114, drifts through space just 7.3 light-years from Earth, close enough that its faint infrared signature appears in sensitive surveys that map the sky for brown dwarf stars and planetary mass objects. This world, roughly 5 times the mass of Jupiter, maintains a surface temperature of negative 48 degrees Celsius, far too cold for liquid water, yet warm enough to suggest an atmosphere still thick with methane clouds and water vapor from its formation billions of years ago. Astronomers estimate that such objects outnumber stars in our galaxy by ratios that strain comprehension. For every sun visible in Earth's night sky, perhaps 10,000 invisible worlds drift through the spaces between stellar systems, carrying no light of their own, detectable only through their gravitational influence on background stars or the faint heat they radiate into space from radioactive decay in their cores. The Milky Way contains perhaps 400 billion stars, suggesting trillions of rogue planets wander through territories so vast that most will never approach another star closely enough to feel its warmth. These calculations assume random ejection velocities and directions, But what if some rogue worlds follow more organized patterns? Galactic rotation creates streams and currents in the distribution of stellar motion, invisible highways that channel objects along preferred trajectories through space. The galactic tide, subtle gravitational effects from the Milky Way's spiral arms and central black hole might influence how rogue planets move through interstellar space, creating coherent flows that persist for millions of years. Recent observations from the Gaia spacecraft, which measures stellar positions with unprecedented precision, reveal that stars don't move randomly through the galaxy, but follow complex streams and associations that trace their common origins in ancient star-forming regions. If stars move in organized patterns, perhaps the planets they occasionally eject do likewise, creating invisible currents of rogue worlds that flow along galactic rotation curves or spiral density waves. The repeating radio signal's source location aligns suspiciously well with one such predicted streamer river of ejected objects that models suggest should flow through the galactic halo at distances where individual stars become impossible to detect. Could the signal originate from a rogue planet following this invisible current? The timing of the bursts, their consistent frequency, their apparent motion through space all hint at something massive enough to maintain complex electromagnetic activity even in the absence of stellar heating. But conventional physics struggles to explain how an isolated planet could generate radio emissions powerful enough to detect across intergalactic distances. Planetary magnetic fields, even the strongest ones found in our solar system, lack the energy to broadcast at such intensities. The most magnetic planet known, the ice giant Uranus, generates radio waves barely detectable beyond the orbit of its outermost moon. Jupiter's emissions reach Earth only because of the intimate dance between its magnetic field and the volcanic activity of its moon, Io, creating electrical currents that accelerate charged particles to relativistic speeds. What mechanism could provide similar energy to a world drifting alone through interstellar space? Perhaps capture of a highly magnetic moon, torn from another star system during the gravitational chaos that ejected both objects into the cosmic void. Such a binary system rogue planet and captured satellite might maintain tidal interactions powerful enough to drive electromagnetic phenomena across cosmic timescales. The 16.35-day period matches no known planetary rotation, but it falls within the range of orbital periods for large moons around gas giant planets. Or perhaps the signal indicates something even more exotic: technological emissions from a civilization that survived planetary ejection, maintaining artificial energy sources and communication systems during their world's journey through the galaxy. The precision of the timing, the choice of transmission frequency, the persistence across millions of years all suggest purpose rather than natural process. Yet the vast energies involved challenge any reasonable assessment of technological capability, requiring power generation on scales that dwarf anything in human experience. The mathematics grow more complex with each observation, requiring new categories of celestial mechanics to describe objects that wander through space, unbound by any star's influence, following trajectories determined by galactic rotation, dark matter distribution, and gravitational interactions with massive structures that remain largely invisible and poorly understood. Each possibility leads to calculations that push the boundaries of current knowledge, revealing how little astronomers truly understand about the universe's most remote and isolated objects. Only continued observation will reveal whether this mathematical mystery represents natural phenomenon or something unprecedented in the catalogue of cosmic radio sources. Meanwhile, the signal maintains its patient rhythm, broadcasting across the void with mechanical precision that suggests either exotic physics or exotic purpose, neither of which fits comfortably into current theoretical frameworks for how rogue worlds should behave during their eternal journey between the stars. The first interstellar visitor announced itself with the gravity of mathematics rather than the drama of discovery. On October 19, 2017, astronomers at the Haleakala Observatory in Hawaii noticed an object moving through the solar system with a trajectory that belonged to no known category of celestial mechanics. The object, initially designated A2017U1 and later renamed Oumuamua, a Hawaiian word meaning messenger from afar arriving first, followed a hyperbolic path that indicated origins beyond the gravitational influence of our Sun. Oumuamua measured roughly 400 meters in length and perhaps 40 meters in width, tumbling end over end through space in a rotation that suggested violent history. Its surface reflected sunlight with the dark efficiency of charcoal, indicating composition unlike any asteroid or comet previously observed in our solar system. Most remarkably, the object showed no signs of outgassing as it approached the Sun, no tail of sublimating ice, no coma of vaporized material, no brightening that would indicate volatile compounds responding to solar heating. Spectroscopic analysis revealed absorption lines consistent with organic compounds, complex carbon-based molecules that form in the cold depths of interstellar space, where ultraviolet radiation from distant stars slowly converts simple hydrocarbons into more elaborate chemical structures. These molecules, called tholins by planetary scientists, create the reddish coloration seen on the surfaces of distant Kuiper Belt objects and the organic haze in Titan's atmosphere. Oumuamua's surface bore the chemical fingerprints of millions of years in interstellar space, bombarded by cosmic rays and bathed in the diffuse radiation field that fills the void between stars. But Oumuamua carried more than just organic chemistry. Detailed observations revealed trace amounts of metallic elements iron, nickel, and heavier elements that require stellar nucleosynthesis to create. These signatures told a story of formation around a star very different from our Sun, perhaps a more massive star that burned through its nuclear fuel quickly and died in a supernova explosion, scattering heavy elements into space where they eventually condensed into planetesimals and minor planets in a stellar system now long destroyed. The object's trajectory suggested an origin in the direction of the constellation Lyra, possibly from the vicinity of the bright star Vega. But Vega lies 25 light-years away, meaning Oumuamua would have required 300,000 years to travel from that stellar neighborhood to our solar system, assuming it maintained constant velocity through interstellar space. During such a journey, the object would have been exposed to temperatures barely above absolute zero, cosmic ray bombardment, and the gradual erosion of interstellar dust impacts that sandblast surfaces at velocities measured in tens of kilometers per second. The chemistry preserved in Oumuamua's surface provided a snapshot of conditions in interstellar space during the late Pleistocene epoch on Earth, when ice sheets covered much of North America and modern humans were beginning to migrate out of Africa. The organic compounds detected by Earth-based telescopes formed through processes that operate over millions of years, requiring patience that transforms simple molecules into complex structures through reactions that proceed one photon at a time in the near absolute zero of interstellar space. As Oumuamua approached its closest point to the Sun, instruments detected unexpected acceleration in its trajectory, a slight but measurable change in velocity that could not be explained by gravitational effects alone. This non-gravitational acceleration resembled the rocket effect seen in comets when sublimating ice creates jets that push against the object's motion. but Oumuamua showed no signs of outgassing or tail formation. The acceleration suggested either internal heating from radioactive decay or some exotic mechanism that conventional physics struggled to explain. The visitor's tumbling rotation period of 7.3 hours indicated either collision damage or tidal disruption during its journey through space. Objects formed in isolation typically develop stable rotation states through gravitational interactions with nearby material. But Oumuamua's chaotic tumbling suggested violent history, perhaps ejection from its parent system through close encounter with a gas giant planet, or fragmentation during passage through another star's Oort cloud, or collision with debris during its long journey through the galaxy. Most mysteriously, Oumuamua's chemical composition suggested formation temperatures and pressures inconsistent with any location in our solar system. The object appeared to contain water ice and carbon monoxide in ratios that require formation in regions where stellar radiation levels and dust densities differ significantly from those found in our local stellar neighborhood. These chemical signatures provided clues about stellar formation processes in other parts of the galaxy, regions where heavier elements exist in different proportions than the cosmic mix that gave birth to our sun and planets. Each spectrum obtained during Oumuamua's brief passage through the inner solar system revealed new puzzles about interstellar chemistry and planetary formation processes. The object carried information encoded in its mineral structure about stellar nucleosynthesis, supernova explosions, and planetary system formation that occurred billions of years ago in star-forming regions now dispersed across hundreds of light years. Reading this chemical record required techniques borrowed from meteoritics, geology, and atmospheric chemistry, disciplines that suddenly found themselves essential for understanding visitors from other star systems. The discovery of Oumuamua confirmed theoretical predictions that interstellar objects should regularly transit our solar system, carrying samples of material from distant stellar formation regions. Computer models suggest that such visitors arrive roughly once per year, but most pass undetected because they approach from directions where surveys don't routinely search, or because they lack sufficient size and reflectivity to appear in current sky patrol programs. Follow-up observations tracked Oumuamua until it faded beyond the sensitivity limits of even the largest telescopes, but not before determining its ultimate trajectory. The object will leave our solar system on a path that carries it toward the constellation Pegasus, where it will continue its journey through interstellar space for perhaps millions more years before encountering another star system. Its brief passage through our neighborhood provided humanity's first direct sample of interstellar material, a messenger carrying chemical information about stellar and planetary formation processes from regions of the galaxy that remain otherwise inaccessible to direct observation. The success of detecting Oumuamua encouraged astronomers to design more sensitive surveys capable of finding similar objects during their approach rather than after they begin departing. Such early detection would allow detailed study with spacecraft missions, possibly intercepting interstellar visitors while they remain within range of current propulsion technology. Each such object carries unique information about its stellar system of origin, providing samples of planetary formation processes that operated under different chemical and physical conditions than those that shaped our own cosmic neighborhood. Meanwhile, Oumuamua continues its solitary journey through space, tumbling slowly as it carries its cargo of organic molecules and heavy elements toward another chance encounter with gravity, perhaps billions of years in the future when the galaxy's rotation brings it near another star system, where curious astronomers might detect its passage and wonder about its origins in the cosmic deep. The ejection begins not with violence but with mathematics, a slow accumulation of gravitational perturbations that amplify over millions of orbital periods until chaos overwhelms stability. In a young star system where three gas giants dance in complex resonance around their parent star, planetary orbits gradually shift through gravitational interactions that follow no simple pattern. The innermost giant pulls the middle planet slightly inward during each conjunction, while the outermost world tugs it toward the system's edge, creating oscillations that grow imperceptibly larger with each passing millennium. For 30 million years, this delicate gravitational ballet maintains approximate stability despite the slowly building chaos. The middle planet, a world roughly twice the mass of Jupiter, with a thick atmosphere of hydrogen and helium wrapped around a core of rock and ice, follows an elliptical orbit that carries it between the inner system's asteroid belts and the outer region's comet clouds. Its 4 large moons sweep through complex orbital resonances, their gravitational interactions creating tidal heating that keeps subsurface oceans liquid despite the system's distance from its red dwarf star. The resonance breakdown occurs during what astronomers call the late heavy bombardment phase of stellar system evolution, when remaining planetesimals and debris from planetary formation create a cosmic shooting gallery of gravitational perturbations. A massive comet, perhaps 50 kilometers in diameter, approaches the three-planet system on a trajectory that passes close enough to the middle world to alter its orbital velocity by less than 1 meter per second, a change so small that it would be undetectable to observers, yet sufficient to push the planet's motion across a critical threshold where stability transforms into runaway instability. The cascade unfolds over just 10,000 years, barely an instant in cosmic terms. Each subsequent orbit carries the planet farther from its stable path, creating stronger gravitational interactions with its siblings that accelerate the instability. The outermost planet, following the widest orbit, serves as a gravitational slingshot that adds energy to the middle world's motion during each encounter, while the inner planet's proximity creates resonance effects that pump the wayward world's orbital eccentricity to catastrophic levels. During the final phase of ejection, the planet's orbit becomes so elongated that it approaches within astronomical units of its star during periastron passage, then swings out beyond the orbit of the system's outermost world during a pastron. The gravitational stress tears apart the delicate orbital architecture that once held the system in stable configuration. 2 of the planet's 4 moons spiral inward until tidal forces fragment them into ring systems, while the other 2 escape into independent orbits around the star, becoming minor planets in their own right. The ultimate ejection occurs during a close encounter with the inner gas giant that accelerates the rogue world beyond the system's escape velocity. In a single orbital passage lasting just a few months, gravitational forces add enough kinetic energy to the planet's motion to overcome the star's gravitational binding permanently. The world that once maintained stable orbits for millions of years suddenly finds itself on a hyperbolic trajectory, leading away from its birth star with velocity sufficient to escape not just the stellar system, but eventually the gravitational influence of the entire stellar cluster. As the ejected planet recedes from its former home, surface temperatures begin their inexorable decline toward the background temperature of interstellar space. This star that once provided warmth dwindles to a point of light indistinguishable from other distant suns, while the planet's thick atmosphere starts its long transition from a dynamic weather system to a gradually freezing shell of increasingly inert gases. Atmospheric circulation patterns that once drove storms larger than Earth slow and simplify as temperature gradients flatten and convection currents weaken. The planet carries with it a cargo of ice and rock in its remaining moons. now bound in orbits that will persist for billions of years even in the absence of stellar heating. These natural satellites provide the only significant gravitational interactions the rogue world will experience during its journey through interstellar space, their mutual orbital dynamics creating tidal effects that continue to generate internal heat long after the parent star's warmth becomes just a memory preserved in slowly cooling atmospheric layers. Magnetic field strength initially remains robust as the planet's metallic core continues generating electrical currents through convection and rotation, but the field gradually weakens as core temperatures drop and convection patterns slow. The magnetosphere that once protected the planet from stellar wind and cosmic radiation contracts closer to the surface, eventually providing only minimal shielding against the interstellar medium's charged particles and high-energy photons. During the first million years of exile, the planet's escape trajectory carries it through the outer regions of its birth stellar system, where gravitational interactions with distant Kuiper belt objects and Oort cloud comets provide final opportunities for capturing additional material. Some asteroids and comets find themselves gravitationally bound to the rogue world, becoming satellites in highly elliptical orbits that will accompany the planet on its journey through the galaxy. The ejection velocity, approximately 47 kilometers per second relative to the system's center of mass, determines the planet's future trajectory through galactic space. This speed exceeds the local stellar group's escape velocity, meaning the rogue world will eventually leave its birth cluster entirely and join the population of objects that wander freely through the galaxy's spiral arms. Computer simulations suggest the planet will require approximately 2 million years to clear the gravitational influence of nearby stars and begin truly independent motion through interstellar space. As the last gravitational ties to its origin system finally break, the planet becomes a citizen of the galaxy rather than any particular stellar system. Its trajectory through space will be influenced by the Milky Way's rotation, the gravitational effects of spiral density waves, and occasional distant encounters with other star systems, but never again will it experience the stable orbital dance that characterized its first 30 million years of existence. The violence of ejection leaves no lasting scars on the planet's surface. The gravitational forces involved operate too slowly to create seismic disruption or atmospheric loss. Instead, the world begins its interstellar journey essentially intact, carrying its atmosphere, magnetic field, and remaining moons into the cosmic deep, where it will spend the next several billion years slowly cooling while traveling distances that dwarf the size of stellar systems. Only the changing sky provides evidence of the catastrophic orbital transformation. Constellations that remained fixed for millions of years begin their slow drift across the celestial sphere as the planet's motion carries it away from familiar stellar neighborhoods toward regions of the galaxy where different stars dominate the night sky, and unknown cosmic phenomena await discovery in the spaces between solar systems. The ejected world joins countless similar refugees from gravitational chaos, adding to the invisible population of rogue planets that astronomers estimate may outnumber stars throughout the galaxy. Each such world carries its own story of orbital instability and gravitational exile, creating a vast diaspora of homeless planets wandering through the cosmic dark with only the faint heat of radioactive decay and tidal interactions to sustain whatever processes continue operating in the absence of stellar energy. In the profound silence that follows ejection, temperature becomes the planet's most fundamental constraint and its most persistent enemy. The world that once basked in stellar radiation, sufficient to maintain atmospheric dynamics and weather patterns, now faces the inexorable thermodynamic reality of interstellar space, where the cosmic microwave background provides the only external energy source, a feeble 2.7 Kelvin that barely distinguishes empty space from absolute zero. Surface temperatures plummet with mathematical precision that follows the Stefan-Boltzmann law, radiating the planet's stored thermal energy into the void at rates determined by surface area and emissivity. Within the first 1,000 years of exile, atmospheric temperatures at the cloud tops drop below the freezing point of carbon dioxide, creating vast sheets of dry ice that begin accumulating in the planet's polar regions and high-altitude atmospheric layers. The once dynamic weather systems that drove circulation patterns across hemispheres slow to nearly imperceptible flows as temperature gradients flatten and convection currents lose their driving force. But beneath the surface, a different thermal story unfolds with the patience of geological time. The planet's core, formed through the gravitational collapse of iron and nickel during its birth in the stellar nebula 4 billion years ago, maintains temperatures approaching 6,000 Kelvin through the slow decay of radioactive isotopes embedded in its metallic structure. Uranium-238, with its half-life of 4.5 billion years, provides a steady flux of alpha particles that heat the surrounding material through electromagnetic interactions. Thorium-230 contributes additional thermal energy with an even longer half-life of 14 billion years, ensuring that internal heating will persist long after the universe itself grows cold and dark. This radioactive furnace operates with the reliability of atomic physics, immune to the external conditions that govern surface temperatures. Each uranium nucleus that undergoes spontaneous fission releases approximately 200 million electron volts of energy, a minuscule amount on human scales, but enormous when multiplied by the countless trillions of radioactive atoms distributed throughout the planet's interior. The cumulative effect maintains core temperatures sufficient to drive convection in the metallic core and lower mantle, preserving magnetic field generation and geological activity even in the absence of tidal heating from a nearby star. The temperature gradient between the blazing core and the frozen surface creates a stable regime of internal heat transport that operates through conduction and convection in the rocky mantle. Thermal energy flows outward from the radioactive core through crystalline rock structures at rates measured in millimeters per year, eventually reaching the surface where it radiates into space as infrared radiation, invisible to optical telescopes but detectable by sensitive thermal imaging systems. This geothermal flux amounts to perhaps 0.1 watts per square meter, 10,000 times weaker than solar heating on Earth, yet sufficient to maintain subsurface temperatures above freezing in regions where liquid water can persist. The planet's thick atmosphere, inherited from its formation in the outer regions of its birth star system, provides crucial insulation that traps geothermal energy near the surface, hydrogen and helium. The primary atmospheric constituents possess low thermal conductivity that creates an insulating blanket effect. As surface temperatures drop below the condensation points of heavier atmospheric components, methane and ammonia begin forming clouds and precipitation that further complicate the thermal structure of the lower atmosphere. Beneath ice caps that grow thicker with each passing millennium, pockets of liquid water persist wherever geothermal heating creates locally elevated temperatures. These subsurface oceans, similar to those detected beneath the ice shells of Jupiter's moon Europa and Saturn's moon Enceladus, maintain thermal equilibria that balance heat input from radioactive decay against heat loss through conduction to the frozen surface layers. The physics of these hidden seas operates independently of external stellar heating, creating isolated ecosystems that could theoretically support chemical processes and even biological activity throughout the planet's journey through interstellar space. Tidal heating from the planet's remaining moons provides additional thermal energy that supplements radioactive decay in driving internal geological processes. The orbital resonances between satellites create periodic gravitational stress that flexes the planet's interior, converting orbital mechanical energy into heat through friction and elastic deformation. This mechanism operates with particular efficiency during close approaches to other massive objects, rare encounters with rogue asteroids, or distant passes near other star systems that temporarily perturb the Moon's orbits and enhance tidal effects. The planet's magnetic field, generated by convection in its liquid metallic core, persists at roughly half the strength it maintained during its stellar-bound existence. The reduced field intensity reflects slower convection rates in the cooling core, but remains sufficient to deflect most cosmic ray particles and solar wind from other stars encountered during the planet's galactic journey. This magnetic shielding protects any remaining atmosphere from gradual erosion by charged particle bombardment, preserving the insulating properties that help maintain subsurface temperatures. Computer models of planetary thermal evolution suggest that this rogue world will maintain subsurface liquid water for several billion years, possibly longer than the remaining main sequence lifetime of its birth star. The radioactive elements that fuel internal heating will continue their decay processes according to physical laws that operate independently of stellar proximity, environmental conditions, or galactic location. Even as the universe expands and cools, eventually reaching temperatures lower than the current cosmic microwave background, these internal heat sources will persist. The thermal isolation of interstellar space creates conditions where energy conservation becomes nearly perfect, unlike planets orbiting active stars, where complex radiative and convective heat transfer mechanisms create rapid temperature fluctuations. The rogue world exists in an environment where thermal changes occur over millions of years. This stability allows for the development of thermal equilibria that persist across cosmic timescales, creating consistent subsurface conditions that remain nearly constant for durations longer than the evolution of complex life on Earth. Surface ice layers function as both thermal insulation and geological records, preserving information about the planet's thermal history in crystalline structures that reflect temperature and pressure conditions during their formation. These ice sheets, potentially hundreds of meters thick in polar regions, create pressure-induced liquid layers at their bases where temperatures rise above the melting point despite surface conditions hundreds of degrees below freezing. The deep freeze transforms the planet's surface into a landscape unlike anything found in stellar systems. Atmospheric gases condense into solid deposits that accumulate in vast plains of crystalline nitrogen, methane, and carbon dioxide. These frozen seas create unique geological features, dunes of solid xenon, mountain ranges of crystallized argon, impact craters filled with frozen noble gases that preserve records of the planet's journey through different regions of interstellar space, where gas densities and chemical compositions vary with galactic location. Yet beneath this alien surface, the planet maintains an interior that resembles worlds still bound to stars. Radioactive decay ensures that core temperatures remain sufficient for geological processes, magnetic field generation, and the maintenance of subsurface oceans where complex chemistry continues operating according to the same physical laws that govern planetary interiors throughout the universe. The rogue world discovers that life requires energy, not necessarily starlight, and that thermal energy from atomic decay provides as reliable a foundation for planetary habitability as fusion reactions in distant stellar cores. The search for invisible wanderers requires techniques that push observational astronomy to its theoretical limits, relying on gravitational effects so subtle that their detection demands precision measurements across years of patient observation. Gravitational microlensing, the most sensitive method for finding dark objects drifting through space, exploits Einstein's prediction that massive bodies bend the fabric of space-time sufficiently to focus light from background sources like cosmic magnifying glasses. When a rogue planet passes precisely between Earth and a distant star, its gravitational field briefly amplifies the star's apparent brightness in a characteristic pattern that reveals both the planet's mass and its trajectory through space. The effect requires extraordinary geometric precision. The alignment between Earth, the lensing planet, and the background star must be accurate to within microarcseconds angular measurements, so small that they correspond to the width of a human hair viewed from a distance of several thousand kilometers. Such perfect alignments occur purely by chance, with probabilities so low that astronomers must monitor millions of stars simultaneously to detect even a few microlensing events each year. The technique transforms astronomy into a statistical enterprise where success depends on observing vast numbers of stars for extended periods, waiting for the rare moments when invisible objects reveal themselves through their gravitational influence. When microlensing occurs, the light curve follows a predictable mathematical form that depends on the lensing object's mass, distance, and velocity. A typical event begins with barely detectable brightening that increases over several days or weeks, reaches maximum amplification when the alignment becomes most precise, then gradually returns to baseline brightness as the rogue planet continues its motion across the sky. The entire event duration, combined with the peak brightness enhancement and the precise shape of the light curve, provides enough information to calculate the planet's mass and distance with remarkable accuracy. The optical gravitational lensing experiment, operating from Las Campanas Observatory in Chile's Atacama Desert, maintains continuous surveillance of dense star fields toward the galactic center, where the high stellar density maximizes the probability of detecting chance alignments. Each night, robotic telescopes photograph millions of stars, comparing their brightness to previous observations with photometric precision approaching 1 part in 10,000. Computer algorithms scan these databases for the characteristic brightening patterns that indicate gravitational lensing, filtering out the much more common brightness variations caused by stellar pulsations, eclipsing binary systems, and instrumental effects. Most remarkably, gravitational microlensing can detect planets smaller than Earth at distances spanning the entire galaxy. Unlike other detection methods that require planets to orbit nearby stars or transit across stellar disks as viewed from Earth, microlensing works equally well for objects in the galactic center, the spiral arms, or the sparsely populated halo regions where rogue planets might accumulate after ejection from their birth systems. The technique provides humanity's only practical method for conducting a census of dark objects throughout the Milky Way, revealing a population of invisible worlds that vastly outnumbers the planets, detectable through conventional astronomical surveys. The first confirmed rogue planet discovered through microlensing, designated Ogla 2012 BLG09 Feverelb, revealed itself during a 35-day brightening event that amplified a background star's light by a factor of 3. Analysis of the light curve indicated a planet roughly 13 times the mass of Earth, located approximately 17,000 light-years away in the direction of the galactic center. The object showed no evidence of gravitational binding to any star, suggesting either a true rogue planet ejected from its birth system or a planet orbiting a star too faint and distant to detect through current observational methods. Follow-up observations using space-based telescopes attempted to identify any possible host star that might have escaped ground-based detection, but found only empty space at the calculated position of the lensing object. The absence of stellar emission across the entire electromagnetic spectrum, from radio waves to gamma rays, confirmed that the planet either orbits a completely dark object, perhaps a brown dwarf too cool to emit detectable radiation, or wanders through space unbound by any gravitational anchor except the galaxy itself. Subsequent microlensing surveys have revealed dozens of similar objects with masses ranging from slightly smaller than Earth to several times larger than Jupiter. The distribution of detected masses suggests that rogue planets span the entire range of planetary sizes, from terrestrial worlds comparable to the rocky planets in our solar system to gas giants that rival the largest planets known to orbit other stars. Each detection adds another data point to the emerging picture of a galaxy, populated by countless invisible worlds drifting through the spaces between stellar systems. The frequency of micro-lensing detections allows astronomers to estimate the total population of rogue planets throughout the galaxy. Statistical analysis of survey results suggests that free-floating planets may outnumber stars by ratios approaching 10 to 1, implying that the Milky Way contains perhaps 4 trillion rogue worlds, more than the total number of planets currently orbiting stars in stable planetary systems. This invisible population represents a significant fraction of the galaxy's total mass in planetary scale objects, creating a previously unknown category of cosmic constituents that influences galactic structure and evolution. But microlensing observations reveal only the shadows of these worlds, providing mass estimates and approximate distances without direct information about their physical properties, atmospheric composition, or thermal characteristics. The lensing effect depends only on gravitational field strength, which correlates with mass regardless of the object's temperature, chemical composition, or internal structure. A cold rogue planet produces identical lensing signatures to a warm planet of the same mass, making it impossible to distinguish between recently ejected worlds that still retain internal heat and ancient wanderers that have cooled to near interstellar temperatures. The geometric requirements for microlensing also mean that each rogue planet can be detected only once, during the brief period when it passes precisely between Earth and a background star, unlike planets orbiting nearby stars, which can be studied repeatedly as they complete multiple orbital periods. Rogue planets revealed through microlensing disappear forever from observational reach once the lensing event concludes. This limitation forces astronomers to extract maximum information from each detection, using sophisticated analysis techniques to squeeze every possible detail from the brief moment when gravity makes the invisible temporarily visible. Advanced micro-lensing surveys now operate with networks of telescopes distributed across multiple continents, providing continuous monitoring that eliminates gaps caused by Earth's rotation and weather conditions. The Korean Microlensing Telescope Network maintains stations in Chile, South Africa, and Australia, ensuring that potential lensing events receive round-the-clock observation during their critical phases. Space-based missions like the Nancy Grace Roman Space Telescope will extend microlensing surveys beyond Earth's atmospheric limitations, potentially detecting rogue planets with masses as small as Mars throughout the galaxy's spiral arms and halo regions. Each newly detected rogue planet raises fundamental questions about planetary formation and stellar system evolution that challenge current theoretical models. How many planets suffer ejection during the chaotic early phases of stellar system development? Do rogue planets retain atmospheric envelopes during their journey through interstellar space? Can such worlds maintain internal heat sources sufficient to support subsurface oceans and possibly even biological activity? The shadows cast by gravitational lensing provide tantalizing hints about these invisible worlds, but answering such questions will require observational techniques that can study rogue planets directly rather than merely detecting their gravitational influence on background starlight. Meanwhile, the survey for gravitational shadows continues with mechanical patience, monitoring millions of stars night after night in search of the brief moments when invisible wanderers reveal their presence through the cosmic spotlight of gravitational lensing. Each detection confirms that our galaxy contains far more worlds than the planets visible around nearby stars, creating a vast diaspora of homeless planets that drift through the cosmic dark, carrying whatever secrets their surfaces and interiors preserve from their violent origins in stellar systems now scattered across thousands of light years. Not all interstellar visitors escape into the galactic deep. Some find themselves captured by gravitational encounters with our solar system's outermost regions, joining the slow orbital dance of objects that inhabit the Kuiper belt and Oort cloud, in elliptical paths so elongated they require thousands of years to complete single revolutions around the Sun. These captured wanderers become permanent residents of our stellar neighborhood, their original interstellar trajectories transformed into bound orbits through gravitational interactions that operate with the precision of celestial mechanics and the randomness of cosmic chance. The capture process requires extraordinary timing and geometric precision. An interstellar object approaching our solar system typically moves too fast to be gravitationally bound by the Sun's influence. Alone escape velocities from the outer solar system exceed 40 kilometers per second. While most rogue planets and asteroids travel through interstellar space at speeds between 20 and 60 kilometers per second relative to nearby star systems. Direct capture through simple gravitational deceleration occurs only when visitors approach with velocities very close to the minimum required for escape, creating narrow windows of opportunity that depend on approach angle, timing, and the gravitational assistance provided by outer planets. More commonly, capture occurs through the three-body gravitational interactions that dominate the dynamics of the outer solar system. When an interstellar object passes near Jupiter or Saturn during their orbital motion around the Sun, the complex gravitational field created by the planet-Sun system can alter the visitor's trajectory in ways that reduce its velocity below escape speed. These encounters operate like gravitational slingshots in reverse, extracting kinetic energy from the visitor's motion and transferring it to the planet's orbital momentum in exchanges so small they produce no measurable effect on planetary orbits, but sufficient to trap previously unbound objects in solar orbit. The mathematics of orbital capture create a natural selection process that favors certain types of interstellar visitors over others. Objects approaching from the direction of the solar system's motion through the galaxy, the apex direction toward which our Sun travels at approximately 26 kilometers per second, encounter our planetary system with reduced relative velocities that facilitate gravitational binding. Conversely, objects approaching from the opposite direction. The antipexes carry additional kinetic energy that makes capture extremely unlikely, even with optimal planetary encounters. Computer simulations of this capture process suggest that our solar system accumulates perhaps one interstellar object every few million years. adding these cosmic immigrants to the population of native asteroids and comets formed during the solar nebula's collapse 4.5 billion years ago. Over the solar system's entire history, several hundred such objects might have joined the outer regions where their highly elliptical orbits carry them between the inner solar system and distances approaching 1 light-year from the Sun. These captured visitors occupy orbital territories beyond Neptune, where their presence becomes nearly impossible to distinguish from native Kuiper Belt objects and Oort cloud comets. Both populations consist of small, dark bodies composed primarily of rock and ice, following highly eccentric orbits that carry them through the same regions of space at velocities that differ by only a few kilometers per second. Only detailed chemical analysis of surface composition and isotopic ratios can reveal which objects formed in our solar nebula and which originated around distant stars, carrying alien chemistry that preserves records of stellar nucleosynthesis processes operating under different conditions billions of years ago. The recently discovered object 2II Borisov, the second confirmed interstellar visitor detected passing through our solar system, demonstrated how such capture might occur, unlike Oumuamua, which followed a hyperbolic trajectory that carried it permanently beyond solar gravitational influence. 2I Borisov's path brought it within 3 astronomical units of the Sun, close enough for detailed spectroscopic analysis that revealed chemical compositions unlike any native solar system object. Observations of 2I Borisov showed water vapor, carbon monoxide, and organic compounds sublimating from its surface as solar heating activated volatile materials that had remained frozen during millions of years in interstellar space. The isotopic ratios of these compounds indicated formation around a star with different metallicity than our Sun, suggesting origins in a stellar system where heavier elements existed in proportions that created different planetary formation conditions. Had 2I Borisov approached our solar system from a slightly different direction, or encountered Jupiter during a different phase of its orbital cycle, gravitational perturbations might have reduced its velocity sufficiently to trap it in a bound orbit around the Sun. Such captured objects would gradually migrate inward through gravitational interactions with the giant planets, their orbits slowly circularizing through processes that operate over millions of years. During close approaches to Jupiter or Saturn, additional gravitational perturbations would continue modifying their trajectories, sometimes ejecting them back into interstellar space, sometimes moving them into more stable orbits in the inner Kuiper Belt where they might persist for billions of years as permanent additions to our solar system's inventory. The captured population includes objects spanning the entire range of sizes found among interstellar wanderers, from asteroid-scale fragments a few kilometers in diameter to rogue planets potentially massive enough to perturb the orbits of native outer solar system objects. The largest captured objects might remain undetected in the Oort cloud's most distant regions, following orbits so elongated that they approach the Sun only once every few million years, spending most of their time at distances where even the most sensitive telescopes cannot detect their presence. Recent observations from the Hubble Space Telescope and ground-based surveys have identified several candidate objects with orbital characteristics suggesting possible interstellar origins. These objects follow trajectories that carry them far beyond the typical orbital distances of native Kuiper Belt objects, with orbital inclinations and eccentricities that indicate capture rather than formation within our solar nebula. Detailed spectroscopic analysis might eventually reveal chemical fingerprints that confirm their alien origins, but such observations require catching these objects during their rare close approaches when they become bright enough for detailed study. The prospect of captured interstellar visitors raises intriguing possibilities for sample return missions that could bring alien material to Earth for laboratory analysis. Unlike the brief passages of objects like Oumuamua and 2I Borisov, which provide only limited opportunities for remote observation, captured objects remain gravitationally bound and accessible for spacecraft rendezvous missions. Such encounters would allow direct sampling of material formed around other stars, providing ground truth for theory about planetary formation processes operating under different stellar conditions throughout the galaxy. The New Horizons spacecraft, after its successful flyby of Pluto and the Kuiper Belt object Arakoth, continues its journey toward the outer solar system, where it might eventually encounter objects of interstellar origin. Although the spacecraft lacks sufficient fuel for major trajectory changes, its instruments remain capable of detecting and characterizing objects that approach its flight path, potentially providing humanity's first close-up observations of captured interstellar material. Meanwhile, the search continues for additional members of our solar system's immigrant population, using orbital analysis and chemical fingerprinting to identify objects that carry the signatures of formation around distant stars. Each discovery adds to the growing catalogue of evidence that stellar systems regularly exchange material through gravitational processes that operate across cosmic distances and timescales, creating a galactic-scale circulation of planetary building blocks that connect star formation regions throughout the Milky Way. The captured visitors serve as permanent ambassadors from other stellar systems, carrying samples of alien chemistry and planetary formation processes that remain accessible for study throughout our solar system's remaining lifetime. Their presence transforms our local stellar neighborhood from an isolated island of planets and asteroids into a crossroads where material from across the galaxy accumulates through gravitational capture, creating opportunities for comparative planetary science that extends far beyond the chemical and physical conditions that shaped our native worlds. The spectroscope becomes humanity's most powerful tool for reading the chemical autobiography written in starlight reflected from wandering worlds. Each photon carries information encoded in absorption lines that reveal the elemental composition, isotopic ratios, and molecular structures present in the surface materials of objects formed around distant stars billions of years ago. When sunlight strikes an interstellar visitor and reflects toward Earth, it passes through whatever thin atmosphere or surface compounds exist on the object, creating absorption features that serve as fingerprints, identifying specific atoms and molecules present in concentrations measured in parts per million. The technique requires extraordinary precision in measuring wavelengths of light to accuracies approaching 1 part in 10 million. Modern spectrographs achieve this resolution through combinations of diffraction gratings, Echelle spectrometers, and interferometric techniques that spread incoming light across thousands of individual detector elements, each sensitive to slightly different wavelengths across the electromagnetic spectrum. The resulting spectra appear as rainbow patterns crossed by dark absorption lines at specific wavelengths where atoms and molecules have removed photons from the reflected sunlight. Each element in the periodic table creates its own unique pattern of absorption lines, determined by the quantum mechanical energy levels of electrons orbiting atomic nuclei. Hydrogen produces a simple series of lines in the visible spectrum, while heavier elements like iron generate hundreds of absorption features spread across ultraviolet, visible, and near-infrared wavelengths. The relative strengths of these lines reveal not only which elements are present, but also their relative abundances, providing quantitative measurements of chemical composition that can be compared to the known ratios found in our solar system and other stellar environments. But the most revealing information comes from isotopic analysis measurements of the relative abundances of different versions of the same element that contain varying numbers of neutrons in their atomic nuclei. Isotopic ratios preserve records of the nuclear physics processes that created heavy elements through stellar nucleosynthesis, supernova explosions, and neutron star mergers. These ratios vary significantly between different stellar formation environments depending on the masses of the stars involved, the timescales of element production, and the efficiency of mixing processes that distribute newly synthesized elements throughout stellar formation regions. The deuterium to hydrogen ratio provides particularly sensitive information about formation conditions because deuterium, created primarily during the first few minutes after the Big Bang, is gradually destroyed by nuclear fusion reactions in stellar interiors. Objects formed in stellar systems with long histories of stellar recycling show lower deuterium abundances than material formed in regions where star formation began more recently. These measurements allow astronomers to estimate the age and stellar enrichment history of the galactic regions where interstellar visitors originated. Carbon isotope ratios tell different stories about the types of stars that contributed to the chemical evolution of alien stellar systems. Carbon-12 dominates in material processed through the nuclear fusion reactions that power low-mass stars like our Sun, while Carbon-13 becomes enhanced in regions where massive stars have undergone supernova explosions that scatter the products of carbon burning and oxygen burning into the interstellar medium. The ratio between these isotopes provides clues about whether an object formed in a stellar association dominated by low-mass stars, or in a region where massive star formation created different patterns of chemical enrichment. Oxygen isotope measurements reveal information about the water ice and rocky minerals present in interstellar objects. Because different stellar nucleosynthesis processes produce oxygen, 16-oxygen-17 and oxygen-18 in varying proportions. These ratios reflect the balance between nuclear fusion in massive stars, explosive nucleosynthesis during supernovae, and neutron capture processes that occur in the extreme environments around neutron stars and black holes. Objects formed in stellar systems with different mixtures of stellar types carry distinctive oxygen isotope signatures that persist throughout their journeys across galactic distances. The discovery of organic compounds on interstellar visitors provides the most complex chemical information, revealing molecular structures that form through radiation-driven chemistry, operating over millions of years in the near-absolute zero conditions of interstellar space. These compounds, called polycyclic aromatic hydrocarbons and complex organic molecules, absorb and emit light at specific wavelengths that create distinctive spectroscopic features in both absorption and fluorescence. Their presence indicates that complex chemistry continues operating in environments far removed from the warm, dense conditions typically associated with organic molecule formation. Spectroscopic analysis of Oumuamua revealed absorption features consistent with organic compounds containing carbon-hydrogen and carbon-carbon bonds, but the object's rapid rotation and distance from Earth prevented detailed molecular identification. The organic signatures suggested surface compositions similar to the carbonaceous chondrite meteorites found on Earth, but with subtle differences in molecular structure that indicated formation under different temperature and radiation conditions than those experienced by asteroids in our solar system. More detailed spectroscopic observations of Borisov provided the first comprehensive chemical analysis of an active interstellar comet. As the object approached the Sun and began sublimating volatile compounds from its surface, spectrographs detected water vapor, carbon monoxide, cyanide radicals, and numerous organic molecules in the temporary atmosphere created by solar heating. The isotopic ratios of these compounds differed significantly from those found in native solar system comets, confirming that 2I Borisov formed around a star with different metallicity and stellar evolution history than our Sun. The carbon monoxide to water ratio in 2I Borisov's coma exceeded values found in any known solar system comet by factors of several 100%, suggesting formation in a stellar system where carbon-rich dust grains dominated the planetary formation process. This chemical signature indicates origins around a star that underwent more extensive carbon dredge-up during its evolution, creating dust grains with higher carbon-to-oxygen ratios than the silicate-dominated materials that formed the rocky planets and asteroids in our solar system. Advanced spectroscopic techniques now under development will extend chemical archaeology to much fainter objects and more complex molecular analysis. The James Webb Space Telescope's infrared spectrograph can detect organic compounds and water ice on objects too small and distant for ground-based observation, while next-generation extremely large telescopes will provide sufficient light-gathering power to obtain detailed spectra of interstellar visitors during their brief passages through the inner solar system. Each spectroscopic measurement adds another piece to the growing catalogue of chemical diversity found among objects formed around different types of stars throughout the galaxy. The emerging picture suggests that stellar systems produce planetary building blocks with chemical compositions that vary significantly depending on stellar mass, metallicity, age, and local environment within galactic star-forming regions. These chemical differences influence planetary formation processes, atmospheric evolution, and potentially the development of conditions suitable for biological chemistry. The chemical fingerprints preserved in interstellar visitors provide ground truth for theories about galactic chemical evolution and stellar nucleosynthesis that would otherwise remain purely theoretical. Each object carries samples of material processed through nuclear reactions in stellar cores billions of years ago, offering direct access to the products of stellar alchemy that created the heavy elements essential for planetary formation and biological chemistry throughout the universe. Future spectroscopic surveys will search for increasingly subtle chemical signatures that reveal information about stellar system architecture, planetary migration processes, and the efficiency of chemical mixing during planetary formation. The goal is to develop chemical techniques capable of identifying not just the stellar system of origin for interstellar visitors, but also the specific types of planets and asteroids that existed in those systems, creating a form of remote planetary science that extends across galactic distances through the chemical messages carried by wandering worlds. The galaxy itself flows like a vast river of stars and dark matter, carrying rogue planets along invisible currents that follow the spiral arm's gravitational architecture across distances measured in tens of thousands of light years. These galactic streams operate with the same fluid dynamics that govern terrestrial rivers, creating channels where stellar motion concentrates and eddies, where objects accumulate in slowly rotating pools that persist for hundreds of millions of years. Rogue worlds ejected from stellar systems don't simply disperse randomly through space, but instead follow these cosmic waterways that direct their motion according to the galaxy's large-scale gravitational structure. The Milky Way's spiral arms function as density waves rather than rigid structures, creating regions where stellar formation occurs more frequently and where gravitational forces guide the motion of unbound objects through preferred trajectories. As the galaxy rotates, these spiral density waves sweep through different regions of the galactic disk at velocities that differ from the orbital speeds of individual stars, creating a complex pattern of gravitational focusing and dispersal that channels rogue planets into coherent streams flowing along the spiral arm boundaries. Computer simulations of galactic dynamics reveal how these currents develop through the interaction between the galaxy's gravitational potential and the random velocities imparted to objects during planetary ejection events. Rogue planets ejected from stellar systems in the galaxy's inner regions follow trajectories that carry them outward through the spiral arms, while objects originating in the outer galactic disk tend to follow more circular paths that keep them within specific galactic zones. The net effect creates a circulation pattern where rogue worlds migrate between the galaxy's inner and outer regions over timescales approaching the age of the universe. Dark matter, which comprises roughly 85% of the galaxy's total mass, provides the invisible scaffolding that shapes these stellar streams and planetary currents. Although dark matter interacts only through gravitational forces, its distribution throughout the galactic halo creates potential wells and ridges that guide the motion of ordinary matter over cosmic distances. Rogue planets, despite their small individual masses, follow trajectories determined by this dark matter architecture, just as rivers on Earth follow valleys carved by geological processes operating over millions of years. The local standard of rest. The average motion of stars in our solar neighborhood serves as a reference frame for measuring how individual objects move relative to the galactic current. Our Sun orbits the galactic center at approximately 230 kilometers per second. But this motion includes components that follow the spiral arm rotation, as well as peculiar velocities that carry our stellar system perpendicular to the galactic plane and radially inward and outward from the galactic center. Rogue planets share these large-scale motions while adding their own ejection velocities that can be several tens of kilometers per second in any direction. Recent observations from the Gaia spacecraft, which measures stellar positions and velocities with unprecedented precision, have revealed previously unknown stellar streams that flow through our local galactic neighborhood. These streams consist of stars that share common origins in ancient star clusters or stellar associations that have been gradually dispersed by galactic tidal forces over hundreds of millions of years. The stars in these streams follow nearly parallel trajectories through space, creating moving groups that maintain their identity even as they spread across hundreds of light years. If stars form coherent streams, the planets they occasionally eject should follow similar patterns, creating rivers of rogue worlds that flow along the same trajectories as their parent stellar populations. The timing of planetary ejection events, which typically occur during the first few million years of stellar system evolution, means that rogue planets should preserve the kinematic signatures of their birth stellar associations even billions of years after ejection. These planetary streams would be invisible to direct observation, but detectable through their gravitational effects on other objects or through statistical analysis of rogue planet discovery patterns. The galactic rotation curve, the relationship between orbital velocity and distance from the galactic center, creates differential motion that stretches stellar streams and planetary currents along their orbital paths. Objects in the inner galaxy orbit faster than those in outer regions, causing streams to develop characteristic S-shaped curves as they wrap around the galactic center multiple times during their billion-year orbital periods. This stretching process gradually disperses the objects within each stream, but coherent motion persists for much longer than the individual orbital periods of stars or rogue planets. Vertical oscillations perpendicular to the galactic plane add additional complexity to the motion of rogue planets as they follow trajectories that carry them through the galactic disk multiple times during each orbital period. the gravitational restoring force created by the mass distribution of stars and gas in the galactic disk, causes objects to oscillate above and below the galactic plane, with periods typically ranging from 60 to 100 million years. These vertical motions create opportunities for rogue planets to encounter stellar systems at different galactic heights, potentially leading to gravitational captures or additional ejection events that modify their trajectories. The galaxy's interaction with its satellite galaxies, the Large and Small Magellanic Clouds, the Sagittarius Dwarf Galaxy, and numerous smaller companions creates tidal streams that influence the motion of objects throughout the galactic halo. These satellite galaxies are gradually being torn apart by the Milky Way's gravitational field, creating streams of stars and dark matter that flow through the outer regions where some rogue planets spend portions of their orbital periods. The gravitational perturbations from these tidal streams can alter the trajectories of rogue planets, potentially redirecting objects between different galactic current systems. The supermassive black hole at the galactic center, with its mass of 4 million suns, creates gravitational effects that influence object motion throughout the inner galaxy. Although direct gravitational attraction from the central black hole affects only objects within a few thousand light-years of the galactic center, the black hole's presence shapes the overall gravitational potential that determines orbital characteristics for objects throughout the galaxy. Rogue planets with highly eccentric orbits might experience close encounters with the galactic center that dramatically alter their trajectories, potentially ejecting them from the galaxy entirely or redirecting them into different spiral arm regions. Recent theoretical work suggests that the galaxy's magnetic field might also influence the motion of rogue planets that retain magnetic fields during their journey through interstellar space. Although magnetic forces are much weaker than gravitational effects, they could create subtle perturbations that accumulate over millions of years, gradually modifying planetary trajectories in ways that depend on the strength and orientation of both the galactic magnetic field and the planet's intrinsic magnetic moment. The study of galactic currents and rogue planet streams represents a new frontier in galactic astronomy that combines stellar dynamics, dark matter, physics, and planetary science into unified models of how matter moves through the galaxy over cosmic time. Understanding these currents provides insight into galactic chemical evolution, stellar formation history, and the efficiency of material exchange between different regions of the galaxy. Each rogue planet carries information about its origins encoded in its trajectory through galactic space, creating opportunities to trace the history of stellar formation and planetary system evolution across billions of years of galactic evolution. Future surveys designed to detect rogue planets through gravitational microlensing or direct imaging will provide the observational data needed to map these galactic currents and test theoretical predictions about how rogue worlds move through the cosmic deep. The emerging picture suggests that rogue planets don't wander randomly through space, but instead follow organized patterns that reflect the galaxy's large-scale structure and evolutionary history, creating a form of galactic paleontology written in the trajectories of homeless worlds drifting between the stars. Beneath kilometers of crystalline ice that never feel sunlight, liquid oceans persist in the depths of rogue planets through mechanisms that operate independently of stellar heating. These hidden seas exist in thermal equilibrium maintained by radioactive decay, tidal interactions, and geothermal processes that continue functioning throughout a world's journey across galactic distances. The physics that governs these subsurface oceans resembles the hydrodynamics found beneath the ice shells of Jupiter's moon, Europa, and Saturn's moon Enceladus. but operating on planetary scales where ocean volumes can exceed Earth's total water content by factors of hundreds or thousands. The transition from surface ice to liquid water occurs at depths determined by the balance between geothermal heating from below and heat loss through conduction to the frozen surface layers above. On a typical rogue planet with Earth-like composition and internal structure, this transition depth varies between 10 and 50 kilometers depending on the planet's age, radioactive element abundance, and the insulating properties of the overlying ice. Younger rogue planets, recently ejected from their stellar systems, maintain subsurface oceans at shallower depths because their interiors retain more thermal energy from formation and early geological processes. The pressure at these depths reaches several thousand atmospheres, sufficient to maintain liquid water at temperatures well below the normal freezing point at Earth's surface. This pressure-dependent melting creates conditions where water remains liquid at temperatures approaching -40 degrees Celsius, expanding the thermal range where subsurface oceans can exist. The high pressure also affects the physical properties of the water itself, increasing its density and modifying its convection patterns in ways that influence heat transport and chemical circulation throughout the ocean volume. Convection currents in these buried seas operate through temperature differences created by geothermal heating at the ocean floor and cooling at the ice-water interface above. Warm water rises from regions where radioactive decay or tidal heating elevates temperatures near the rocky core, while cooler water sinks along the ice ceiling where contact with the frozen surface layers extracts thermal energy. These circulation patterns transport heat, dissolved minerals, and chemical compounds throughout the ocean, creating a dynamic system that persists across geological timescales. The rocky cores of rogue planets continue generating heat through radioactive decay of uranium, thorium, and potassium isotopes that will persist for billions of years regardless of external stellar heating. This internal energy source drives hydrothermal activity at the ocean floor similar to the deep-sea vents found in Earth's oceans, where superheated water emerges from the rocky interior, carrying dissolved minerals and chemical compounds that can support complex biochemistry. The energy flux from these hydrothermal systems provides sufficient power to drive chemical reactions and maintain temperature gradients that prevent the oceans from freezing solid. Tidal heating from remaining moons adds additional thermal energy that supplements radioactive decay in maintaining ocean temperatures. Even rogue planets that lost most of their satellite systems during ejection often retain one or more large moons whose orbital motion creates periodic gravitational stress that flexes the planet's interior. This mechanical energy converts to heat through friction and elastic deformation, providing a renewable energy source that operates as long as the orbital resonances between planet and moon remain stable. The chemical composition of subsurface oceans depends on the minerals available for dissolution from the rocky core and the efficiency of circulation processes that transport these materials throughout the liquid volume. Water in contact with basaltic rock gradually dissolves silicates, sulfates, and chlorides that increase the ocean's salinity and modify its freezing temperature. Higher salinity concentrations allow liquid water to persist at even lower temperatures, expanding the range of conditions where subsurface oceans remain stable. The ice-water interface creates unique physical and chemical environments where crystallization and melting processes operate in dynamic equilibrium. Fresh ice forms continuously as heat lost to the surface extracts thermal energy from the uppermost ocean layers, while geothermal heating melts ice at the bottom of the frozen shell. This constant exchange creates layered ice structures with different crystalline properties that preserve records of the ocean's thermal history over millions of years. Some rogue planets might maintain multiple ocean layers separated by high-pressure ice phases that form under the extreme pressures found deep within planetary interiors. Water ice exists in more than a dozen different crystalline forms depending on temperature and pressure conditions, with some phases remaining solid at temperatures where normal ice would melt. These high-pressure ice layers could create isolated ocean compartments at different depths within the planet, each with its own circulation patterns and chemical environment. The possibility of biological activity in rogue planet oceans depends on the availability of chemical energy sources and the stability of conditions suitable for complex organic chemistry. Hydrothermal vents provide environments where chemical gradients between hot, mineral-rich water and cold ocean water create energy sources that could drive metabolic processes. On Earth, similar environments support entire ecosystems based on chemosynthesis rather than photosynthesis, suggesting that life might persist in subsurface oceans even without stellar energy input. The isolation of rogue planet oceans from cosmic radiation and the vacuum of space creates remarkably stable environments where evolutionary processes could operate over billions of years without the periodic mass extinction events that characterize planetary surfaces exposed to asteroid impacts, stellar flares, and other external disturbances. This stability might allow for the development of complex biological systems with evolutionary histories longer than the age of complex life on Earth's surface. Detection of subsurface oceans on rogue planets presents extraordinary observational challenges because the liquid water remains hidden beneath opaque ice shells that emit no distinctive electromagnetic signatures detectable by current astronomical instruments. Gravitational interactions between the liquid ocean and the planet's solid components might create subtle variations in the planet's gravitational field or rotational dynamics that could be measurable through precision astrometry. But such observations would require detecting rogue planets at close range through techniques not yet developed. Future spacecraft missions to captured interstellar objects might provide opportunities to study rogue planet subsurface oceans through direct exploration techniques similar to those proposed for Europa and Enceladus. Ice-penetrating probes could drill through the frozen surface layers to access the liquid water beneath, while orbiting spacecraft could map subsurface ocean structure through gravitational field measurements and radar-sounding techniques that reveal the depth and extent of hidden water reservoirs. The discovery that rogue planets can maintain subsurface oceans for billions of years revolutionizes concepts of planetary habitability by removing the requirement for stellar heating as a prerequisite for liquid water. The hidden seas might represent the most common environments for liquid water in the galaxy, vastly outnumbering the surface oceans found on planets orbiting within their stars' habitable zones. If life can arise and evolve in such environments, the universe might contain biological activity in places previously considered impossible for supporting living systems. Each rogue planet carries its subsurface ocean through galactic space as a self-contained biosphere insulated from external environmental changes by kilometers of protective ice. These mobile worlds might serve as vectors for distributing biological material across galactic distances, carrying life from one stellar system to another during gravitational encounters that could transfer organisms between planetary systems separated by thousands of light years. The possibility transforms rogue planets from barren wastelands into potential oases where life persists in the cosmic deep, hidden beneath frozen surfaces that conceal some of the galaxy's most persistent and protected habitable environments. Time stretches across distances that transform the familiar into the impossible, carrying objects on journeys that span not just light years, but entire geological eras of planetary evolution. an asteroid ejected from the Alpha Centauri system when Earth's continents still clustered together in the supercontinent. Pangaea now approaches our region of space. Having travelled 4.37 light-years at velocities that make continental drift seem rapid by comparison, the object carries within its crystalline structure the chemical memory of stellar processes that operated when trilobites dominated Earth's oceans and the first plants began colonizing dry land. The mathematics of interstellar travel impose constraints that humble human intuition about distance and duration. Even objects moving at exceptional velocities 50 kilometers per second, relative to their stellar systems of origin, require nearly 30,000 years to traverse the distance between our Sun and its nearest stellar neighbour. Most rogue planets and asteroids travel more slowly, following trajectories that require hundreds of thousands or millions of years to cross the voids between stellar systems. These timescales dwarf recorded human history while representing mere moments in the cosmic calendar where stellar evolution operates over billions of years. During such extended journeys, interstellar travelers experience conditions that have no analogue in the environments found within stellar systems. Cosmic ray bombardment gradually alters surface chemistry through nuclear reactions that transmute lighter elements into heavier ones, creating isotopic signatures that record the duration and intensity of exposure galactic radiation fields. Each high-energy proton that strikes an asteroid's surface initiates cascade reactions that produce distinctive patterns of secondary particles and nuclear fragments embedded in the object's crystal lattice. The density of interstellar space, typically 1 hydrogen atom per cubic centimetre, creates a tenuous medium that nonetheless exerts measurable effects on objects travelling at interstellar velocities. Over millions of years, this sparse gas produces erosion patterns and chemical modifications that accumulate into observable surface features. Hydrogen atoms striking rogue planet atmospheres at relative velocities exceeding orbital speeds create auroral phenomena and atmospheric chemistry unlike anything found in gravitationally bound planetary systems. Temperature equilibrium in interstellar space approaches the cosmic microwave background radiation. 7 Kelvin above absolute zero, creating thermal conditions where quantum mechanical effects become significant for understanding material properties. At these temperatures, molecular motion nearly ceases. Crystal structures contract to their minimum possible dimensions, and chemical reaction rates drop to levels where processes requiring thermal activation can require millions of years to reach completion. Yet even in this extreme cold, slow chemistry continues operating through mechanisms that depend on quantum tunneling rather than thermal energy. Hydrogen atoms embedded in ice crystal lattices can migrate through the solid matrix by tunneling through energy barriers that would be insurmountable at higher temperatures, gradually transforming the molecular structure of surface ices over geological time periods. These processes create chemical compounds that exist only under interstellar conditions, forming exotic ices and organic molecules that preserve records of billion-year chemical evolution. The gravitational environment of interstellar space differs fundamentally from conditions within stellar systems, where planets experience constant acceleration toward their parent stars. Rogue planets travel through regions where gravitational fields from individual stars become negligible, creating microgravity conditions where only the galaxy's large-scale gravitational structure provides directional acceleration. This environment allows for the formation of debris fields and satellite systems that follow orbital mechanics impossible near massive stellar objects. Objects that began their interstellar journey during Earth's Archean eon, when the atmosphere contained almost no free oxygen and life consisted entirely of primitive bacteria. now traverse regions of space where the local stellar population has changed significantly through galactic rotation and stellar evolution. The constellations visible from these ancient travelers bear no resemblance to star patterns familiar from Earth, because stellar proper motions have dispersed the original stellar associations into completely different configurations. During their million-year journeys, rogue planets witness stellar events that occur on timescales matching their travel durations. Massive stars evolve from main sequence burning through supergiant phases to supernova explosions within timeframes comparable to interstellar crossing times, allowing rogue worlds to observe complete stellar life cycles from perspectives unavailable to planets bound within stable stellar systems. Some interstellar travelers pass close enough to supernovae to experience the intense radiation and shock waves from stellar explosions, carrying surface modifications and isotopic anomalies that record these catastrophic events. The concept of simultaneity becomes meaningless across interstellar distances where light travel time approaches the duration of entire interstellar journeys. Events occurring now in the Alpha Centauri system happened 4.37 years ago, as measured on Earth, while signals from more distant stellar systems carry information about conditions that existed when human civilization occupied completely different technological and cultural stages. Rogue planets serve as time capsules that preserve chemical and physical records of stellar system conditions from epochs separated by millions of years. Magnetic field interactions during interstellar travel create phenomena that operate over cosmic distances and durations. Rogue planets with persistent magnetic fields gradually accumulate charged particles from the interstellar medium, creating radiation belts and magnetospheric structures that evolve over millions of years of exposure to varying galactic magnetic field orientations. These accumulated particle populations carry information about magnetic field conditions encountered during billion-year journeys through different regions of galactic space. The erosion patterns created by interstellar dust impacts reveal information about the density and composition of material encountered during extended travels through different galactic environments. Dust grain impacts at velocities approaching 20 kilometers per second create microscopic craters and chemical modifications that accumulate into measurable surface features over million-year exposure periods. Analysis of these impact signatures provides archaeological evidence about the distribution of solid material in interstellar space and its variation between different galactic locations. Gravitational interactions with dark matter might create subtle perturbations in rogue planet trajectories that accumulate over million-year travel times into detectable orbital modifications. Although individual dark matter particles interact only weakly with ordinary matter, the cumulative effect of countless interactions during extended interstellar journeys could produce measurable changes in object trajectories that preserve information about dark matter density variations encountered during galactic-scale travels. The thermal history of objects during interstellar travel depends on internal heat sources that operate independently of external stellar radiation. Radioactive decay continues providing internal heating throughout million-year journeys, creating temperature gradients that drive slow geological processes and atmospheric circulation patterns. The balance between internal heat generation and radiative cooling to space determines whether rogue planets maintain subsurface liquid water or freeze completely solid during their travels between stellar systems. Some interstellar travelers might encounter multiple stellar systems during their journeys, receiving temporary heating during close approaches to other stars that briefly activate surface chemistry and atmospheric dynamics before returning to the deep freeze of interstellar space. These thermal cycles create geological and chemical records that preserve information about the stellar systems encountered during million-year odysseys through galactic space. The objects now approaching our solar system from directions that point toward ancient stellar positions carry chemical signatures and surface modifications that record conditions in stellar formation regions that no longer exist in their original configurations. Reading these records requires techniques that combine stellar archaeology, galactic dynamics, and interstellar chemistry into comprehensive models of how matter moves through the galaxy over cosmic timescales that encompass the entire history of stellar evolution and galactic chemical enrichment. The search for invisible wanderers enters a new epoch as technological advancement transforms humanity's ability to detect thermal signatures from objects that emit no reflected starlight. The Nancy Grace Roman Space Telescope, launching in the middle of this decade, carries infrared instruments sensitive enough to detect the faint heat glow from rogue planets warmed by nothing more than radioactive decay in their cores. Unlike optical telescopes that depend on reflected or emitted light, these thermal detectors reveal objects through their temperature signatures, creating opportunities to discover wandering worlds throughout the galaxy's spiral arms and halo regions. Wide-field infrared surveys operate by comparing images taken months apart, searching for objects that move against the background of distant stars and galaxies. Rogue planets reveal themselves through their proper motion, the slow drift across the sky that results from their velocities through space combined with their proximity relative to more distant background sources. Computer algorithms process millions of infrared images, comparing pixel intensities and object positions with mathematical precision that can detect movements smaller than the apparent width of a human hair viewed from several kilometers away. The Vera Rubin Observatory's legacy survey of space and time will photograph the entire visible sky every 3 nights for 10 years, creating a time-lapse movie of cosmic motion that captures asteroids, comets, and potentially rogue planets as they move through our local galactic neighborhood. Each object that shows consistent proper motion over multiple observations becomes a candidate for follow-up study with more sensitive instruments capable of determining distances, masses, and thermal properties through photometric and spectroscopic analysis. Ground-based telescopes equipped with adaptive optic systems now achieve angular resolution that rivals space-based instruments by compensating for atmospheric turbulence in real time. These systems use deformable mirrors controlled by hundreds of actuators that adjust mirror shape thousands of times per second, correcting for atmospheric distortions that normally blur astronomical images. The resulting clarity allows detection of faint infrared sources that would otherwise remain hidden in the noise of atmospheric scintillation and thermal background radiation. Gravitational wave detectors, originally designed to measure distortions in spacetime caused by colliding black holes and neutron stars, might eventually achieve sensitivity sufficient to detect the gravitational effects of rogue planets passing through our local stellar neighborhood. Although individual planets generate gravitational waves too weak for current instruments, next-generation detectors with arm lengths measured in millions of kilometers could potentially sense the space-time curvature created by Jupiter-mass objects moving at interstellar velocities within a few light-years of Earth. Machine learning algorithms trained on synthetic data from computer simulations learn to recognize the subtle patterns that distinguish rogue planets from background stars, asteroids, and instrumental artifacts. These artificial intelligence systems process observational data with pattern recognition capabilities that exceed human analytical capacity, identifying candidate objects in datasets containing millions of sources. The algorithms continue improving their detection accuracy as they encounter new examples, gradually developing sensitivity to increasingly subtle signatures that might indicate exotic objects or unusual orbital characteristics. Citizen science projects distribute astronomical data analysis across thousands of volunteer computers, harnessing collective human pattern recognition to identify objects that automated algorithms might miss. Participants examine images from sky surveys, marking objects that show unusual motion, color, or brightness characteristics that could indicate interstellar visitors or captured rogue planets. This distributed approach has already led to discoveries of brown dwarf stars, asteroid families, and comet-like objects in the outer solar system that professional astronomers might have overlooked. Radio telescopes search for electromagnetic emissions from rogue planets that maintain magnetic fields during their journey through interstellar space. Although most isolated planets generate radio waves too weak for detection at interstellar distances, objects with unusually strong magnetic fields or active satellite systems might produce detectable signals through mechanisms similar to the radio emissions observed from Jupiter and its volcanic moon, Io. The search requires patience and sensitivity. Monitoring millions of potential sources for periodic signals that might indicate planetary rotation or orbital motion in rogue planetary systems. Stellar occultation events provide opportunities to detect rogue planets when they pass directly between Earth and background stars, temporarily blocking starlight in ways that reveal the size and density of the intervening object. These events last only minutes or hours, requiring coordinated observation networks that can respond quickly to predicted occultations or detect unexpected events through continuous monitoring of bright stars. The technique works best for objects in the outer solar system or nearby interstellar space where angular sizes become large enough to create measurable brightness changes. Atmospheric composition analysis of rogue planets will become possible when next-generation space telescopes achieve sufficient sensitivity to obtain spectra from thermally glowing atmospheres. The James Webb Space Telescope can already detect atmospheric components in nearby brown dwarf objects, and similar techniques might reveal the presence of water vapor, methane, or other volatile compounds in the atmospheres of captured interstellar visitors or recently ejected rogue planets that still retain thick gaseous envelopes. Direct imaging of rogue planets requires suppressing the overwhelming brightness of nearby stars to reveal much fainter thermal emissions from planetary objects. Coronagraph instruments and starshade technology developed for detecting exoplanets around other stars will eventually enable direct observation of rogue planets in our local stellar neighborhood. These techniques could reveal surface features, atmospheric dynamics, and temperature distributions on isolated worlds wandering through interstellar space. Space-based interferometry missions will combine light from multiple telescopes to create synthetic apertures with angular resolution equivalent to instruments hundreds of meters in diameter. These systems could potentially resolve surface features on nearby rogue planets, revealing information about geological processes, atmospheric circulation, and even the presence of subsurface oceans through thermal mapping of surface temperature variations. The technique requires extraordinary precision in spacecraft positioning and timing, but offers possibilities for detailed study of interstellar objects impossible with single-dish telescopes. Neutrino detectors might eventually achieve sensitivity sufficient to observe the radioactive decay signatures from rogue planet interiors, revealing information about internal composition and thermal structure through the neutrinos produced by uranium and thorium decay in planetary cores. Although individual neutrino interactions occur rarely, large-scale detectors could potentially accumulate enough events over years of observation to map the internal heat sources that maintain subsurface oceans and geological activity in isolated worlds. Future missions to captured interstellar objects will provide ground truth for remote sensing techniques, while offering opportunities for direct sampling of alien planetary material. Spacecraft equipped with drills, spectrometers, and sample return capabilities could land on rogue asteroids or comets captured in the outer solar system, providing detailed analysis of surface composition, internal structure, and chemical history that preserves records of formation around distant stars billions of years ago. The technological convergence of these diverse detection methods creates a comprehensive survey capability that will reveal the population of dark objects wandering through our galactic neighborhood. Each new discovery adds constraints to theoretical models of planetary formation, stellar system evolution, and galactic chemical enrichment, while providing observational targets for increasingly sophisticated analysis techniques. The hunt for invisible wanderers transforms from speculative possibility to systematic exploration of a previously hidden component of galactic structure. Within the next 2 decades, these advancing technologies will likely provide the first comprehensive census of rogue planets within several hundred light-years of Earth, revealing whether current theoretical predictions about their abundance and characteristics match the reality of objects actually wandering through interstellar space. Each detection will open new questions about planetary formation processes, stellar system dynamics, and the efficiency of gravitational interactions that shape the architecture of planetary systems throughout the galaxy. The success of this technological hunt will determine whether rogue planets represent rare casualties of stellar system evolution or the most common type of planetary object in the galaxy, outnumbering the worlds that remain gravitationally bound to their parent stars and challenging fundamental assumptions about where planetary processes operate in the cosmic deep. The outer reaches of our solar system whisper with gravitational anomalies that suggest the presence of unseen massive objects drifting in orbital territories beyond Neptune's influence. These subtle perturbations in the trajectories of known asteroids and comets create mathematical puzzles that challenge conventional understanding of solar system architecture, hinting at the possibility that captured interstellar wanderers might inhabit the cold darkness where our sun's gravitational influence fades toward the threshold of interstellar space. Orbital resonance patterns among trans-Neptunian objects reveal clustering that statistical analysis suggests cannot result from random gravitational interactions with known planetary masses. The orbits of several dozen asteroids in the distant Kuiper belt show unexpected alignments in their perihelion arguments and orbital inclinations, creating patterns that persist despite the chaotic gravitational environment that should randomize such orientations over millions of years. These orbital correlations require explanation through gravitational influences from massive objects that remain undetected by direct observation. The most compelling evidence emerges from analysis of long-period comets that approach the inner solar system following trajectories that originate in the Oort cloud's most distant regions. Computer models of their orbital evolution reveal perturbations that exceed the gravitational effects expected from known planets, stellar encounters, and galactic tidal forces. The magnitude and direction of these anomalies suggest gravitational shepherding by objects with masses ranging from several Earth masses to perhaps 10 times Jupiter's mass, located at distances between 200 and 2,000 astronomical units from the Sun. Planet 9, the hypothetical super-Earth, whose existence has been inferred from these orbital anomalies, might represent a captured rogue planet, rather than a native member of our solar system. The object's proposed orbital characteristics, including high eccentricity and inclination relative to the plane containing the known planets, resemble the trajectories expected for interstellar objects that underwent partial gravitational capture during encounters with the outer solar system billions of years ago. Such an origin would explain both the orbital properties and the failure of optical surveys to detect an object of planetary mass in the outer solar system. Gravitational perturbation analysis requires extraordinary precision in tracking object positions over decades of observation to reveal the subtle influences of distant massive objects. The technique measures deviations from predicted orbital motion that amount to angular displacements smaller than the apparent size of a coin viewed from distances exceeding 1,000 kilometers. These measurements demand correction for numerous competing effects including relativistic precession, solar radiation pressure, outgassing from comet nuclei, and gravitational influences from asteroid belt objects. Recent observations from the Cassini spacecraft during its final years orbiting Saturn provided independent evidence for anomalous gravitational effects in the outer solar system. Precise tracking of the spacecraft's trajectory revealed unexplained accelerations that could not be attributed to known sources of orbital perturbation, including solar radiation pressure, atmospheric drag, or gravitational effects from Saturn's moons. Although these anomalies remain within measurement uncertainties, they suggest the possibility of additional massive objects in the outer solar system that influence spacecraft trajectories through gravitational attraction. The search for gravitational signatures has expanded to include analysis of asteroid family dispersal patterns and the long-term evolution of comet orbits that provide indirect evidence for massive perturbing objects. Asteroid families created by collisional breakup events should disperse according to predictable patterns, determined by the velocity changes imparted during fragmentation and subsequent gravitational evolution. Observed dispersal patterns for several families exceed theoretical predictions, suggesting additional gravitational influences that accelerate the spreading of fragment orbits beyond rates expected from known planetary perturbations. Stellar occultation timing provides another avenue for detecting massive objects through their gravitational effects on light propagation. When distant stars pass behind the Sun or planets as viewed from Earth, gravitational lensing creates subtle changes in arrival times for photons following slightly different paths through curved space-time. Precision timing of stellar occultations might reveal gravitational lensing effects from massive objects in the outer solar system, although such measurements require timing accuracy approaching nanoseconds and correction for atmospheric effects that introduce much larger timing variations. The gravitational influence of captured rogue planets would extend throughout the outer solar system, creating complex resonance patterns that evolve over millions of years as objects exchange orbital energy through gravitational interactions. These resonances could explain the unusual orbital architecture of trans-Neptunian objects, including the high inclinations and eccentricities that characterize many Kuiper belt objects. Computer simulations suggest that a captured super-Earth could sculpt the observed orbital distribution through repeated gravitational encounters that gradually modify object trajectories. Astrometric surveys designed to detect stellar parallax and proper motion might inadvertently discover massive planets in the outer solar system through their gravitational effects on nearby stars. Although individual planetary masses produce minuscule effects on stellar motion, accumulated observations over decades could reveal periodic wobbles or systematic accelerations that indicate gravitational attraction by unseen solar system objects. Such detection requires measuring stellar positions with accuracy exceeding micro-arc second precision across observational baselines spanning multiple years. The thermal signatures of massive objects in the outer solar system depend on their internal heat sources and atmospheric retention during billions of years in near-interstellar conditions. Captured rogue planets might maintain detectable infrared emissions through radioactive decay or residual formation heat, while native objects formed in the cold outer solar system could remain below detection thresholds for thermal imaging surveys. This difference in thermal properties provides a potential method for distinguishing between captured interstellar visitors and objects that formed within our solar nebula. Recent improvements in orbital determination accuracy have revealed additional candidates for gravitational perturbation analysis, including irregular satellites of the giant planets and objects in highly eccentric orbits that carry them between the inner solar system and Kuiper Belt regions. These objects serve as gravitational probes that sample different regions of the solar system's potential field, providing constraints on the mass distribution and orbital characteristics of any undiscovered massive objects. The possibility that our solar system contains captured rogue planets raises fundamental questions about the efficiency of gravitational capture processes and the prevalence of interstellar objects in our local galactic neighborhood. If massive planets can be captured and retained in stable orbits around the Sun, similar processes might operate around other stellar systems throughout the galaxy, creating a population of adopted worlds that originated in completely different stellar environments. Future surveys using next-generation telescopes and improved computational techniques will provide definitive answers about the existence of massive objects in the outer solar system. The Vera Rubin Observatory and space-based infrared missions will achieve sensitivity and coverage sufficient to detect planetary mass objects throughout the regions where gravitational perturbations suggest their presence. These observations will determine whether the orbital anomalies result from unknown planets, statistical coincidences, or systematic errors in current orbital models. The resolution of these gravitational mysteries will reshape understanding of solar system formation and evolution, while providing insight into the capture dynamics that might retain interstellar visitors in bound orbits around our Sun. Each newly discovered massive object adds constraints to theoretical models of planetary migration, gravitational dynamics, and the efficiency of material exchange between stellar systems across galactic distances. The outer solar system remains a frontier where captured wanderers from other stars might still await discovery in the cold darkness beyond the realm of familiar planets. Each visiting object that passes through our solar system carries within its crystalline structure and chemical composition a compressed library of information about stellar formation, planetary evolution, and the violent history of distant star systems scattered across thousands of light-years of galactic space. These wandering messengers preserve records written in isotopic ratios, mineral structures, and organic compounds that require techniques borrowed from meteoritics, geochemistry, and astrobiology to decode the stories they tell about cosmic processes operating under conditions vastly different from those that shaped our local stellar neighborhood. The isotopic signatures embedded in interstellar visitors provide the most direct evidence about nucleosynthesis processes in their stellar systems of origin. The ratio of magnesium-24 to magnesium-26 reflects the balance between nuclear burning in massive stars and explosive nuclear synthesis during supernova events, while variations in silicon isotope abundances reveal information about the efficiency of oxygen, burning in stellar cores, and the mixing processes that distribute heavy elements throughout stellar formation regions. These ratios serve as cosmic chronometers that record the timing and intensity of stellar evolution episodes that occurred billions of years before the objects began their journey through interstellar space. Crystalline structure analysis reveals thermal histories that preserve information about planetary formation processes operating under different temperature and pressure regimes than those found in our solar system. the size distribution of mineral grains, their crystallographic orientations, and the presence of shock features indicate whether objects form through gradual accretion in cool stellar nebulae or experienced violent collisional disruption during planetary system instabilities. Scanning electron microscopy and X-ray diffraction techniques can distinguish between materials that condense directly from stellar atmospheres and those that underwent subsequent processing in planetary interiors or impact events. Organic compound analysis provides insights into the chemical complexity achievable in different stellar environments, revealing how carbon-based chemistry operates under varying radiation fields, temperature conditions, and elemental abundance patterns. The molecular structures found in interstellar visitors, polycyclic aromatic hydrocarbons, amino acid precursors, and complex carbon chains indicate the efficiency of organic synthesis in environments where stellar ultraviolet radiation, cosmic ray bombardment, and thermal processing create different pathways for chemical evolution than those found in our solar system's formation region. Trace element abundances in meteoritic samples from interstellar objects reveal information about stellar metallicity, supernova enrichment patterns, and the efficiency of chemical mixing during planetary system formation. Elements heavier than iron produced primarily through neutron capture processes in stellar cores, and explosive nucleosynthesis exist in ratios that reflect the balance between different nuclear physics processes operating in massive stars. These heavy element signatures provide constraints on the initial mass function of stars in the formation regions where interstellar visitors originated. Magnetic remnants preserved in metallic components of interstellar objects carries information about magnetic field strengths and orientations in their birth stellar systems. Planetary formation occurs within magnetic environments created by young stellar objects, and these fields influence dust grain alignment, planetesimal collision dynamics, and the efficiency of angular momentum transport during accretionary disk evolution. The magnetic signatures recorded in iron-nickel grains preserve fossil evidence of these ancient magnetic environments, providing constraints on stellar magnetic field evolution and protoplanetary disk physics. Shock metamorphic features in crystalline minerals reveal the impact histories experienced by objects during their formation and subsequent evolution in their birth stellar systems. High-pressure mineral phases, planar deformation features, and melting textures indicate exposure to impact velocities and pressures that reflect the bombardment environment during planetary system formation. Comparison with similar features in lunar samples and meteorites from our solar system provides constraints on the universality of late heavy bombardment phases and collisional evolution processes. Noble gas isotope ratios, particularly helium, neon, and argon signatures, preserve information about stellar wind compositions and solar particle irradiation in ancient stellar systems. These isotopes become trapped in mineral lattices during space weathering processes and solar wind implantation, creating archives of stellar activity and radiation environment conditions that operated billions of years ago. The noble gas signatures can distinguish between objects that formed close to their parent stars and those that originated in colder outer regions where stellar radiation effects remained minimal. Cosmic ray exposure ages calculated from nuclear reaction products reveal the duration of interstellar journeys and provide constraints on ejection velocities and galactic trajectories. Cosmic ray spallation reactions create distinctive isotopic signatures that accumulate during exposure to galactic radiation fields, allowing determination of how long objects spent traveling through interstellar space before entering our solar system. These exposure ages, combined with trajectory analysis, provide information about the timing of ejection events and the galactic regions traversed during interstellar transit. Volatile compound inventories preserved in ice phases and organic matrices reveal information about temperature and chemical conditions in the outer regions of alien stellar systems where comets and icy planetesimals formed. The relative abundances of water, carbon monoxide, methane, and other volatiles reflect equilibrium condensation processes operating at different distances from parent stars with varying luminosities and spectral characteristics. These volatile signatures provide constraints on the habitable zone boundaries and atmospheric evolution processes in planetary systems with different stellar properties. Micrometeorite impact features record the density and velocity distribution of interstellar dust encountered during billion-year journeys through galactic space. The size distribution, chemical composition, and impact velocities of dust grains that created microscopic craters and chemical modifications on object surfaces provide information about interstellar medium properties in different galactic regions. These impact records serve as passive collectors that sample the interstellar environment along the entire trajectory of wandering objects. Radiation damage patterns in crystalline structures reveal the intensity and spectral characteristics of stellar radiation environments in distant stellar systems. High-energy particles and photons create distinctive defects in crystal lattices that accumulate over geological timescales, preserving information about stellar activity levels, flare frequencies, and the radiation shielding provided by planetary magnetic fields and atmospheric envelopes. Analysis of radiation damage requires sophisticated techniques that can distinguish between effects created in birth stellar systems and subsequent exposure during interstellar travel. The search for biosignatures in interstellar visitors represents the ultimate goal of astrobiological investigation, seeking evidence for past or present biological activity in objects that originated around other stars. Although no confirmed biosignatures have been detected in interstellar objects, the possibility remains that captured visitors might carry preserved biological material or chemical evidence of life processes operating in subsurface oceans or hydrothermal environments. Such discoveries would revolutionize understanding of life's distribution throughout the galaxy, while providing direct samples of extraterrestrial biology for laboratory analysis. Each analytical technique applied to interstellar visitors requires adaptation to the unique challenges posed by objects that spent millions of years in the extreme environment of interstellar space. Contamination from terrestrial sources, space weathering effects, and the limited sample sizes available from brief observational opportunities demand development of increasingly sensitive and specific analytical methods. The integration of multiple complementary techniques provides comprehensive characterization that maximizes the scientific return from each precious sample of alien planetary material. The accumulating database of chemical and physical properties from interstellar visitors will eventually provide sufficient statistics to identify patterns that reveal systematic differences between stellar formation environments throughout the galaxy. These comparative studies will constrain models of galactic chemical evolution, stellar nucleosynthesis, and planetary formation processes while identifying the most promising targets for future interstellar exploration missions seeking to study planetary systems around other stars through direct sample return from their wandering representatives. The eternal journey continues without destination or purpose, beyond the simple persistence of motion through space that operates according to gravitational laws older than stellar formation and more fundamental than the temporary arrangements of matter that create galaxies, stars, and the brief episodes of planetary formation that punctuate cosmic history with islands of complexity in an otherwise empty universe. Rogue planets drift through the cosmic deep as witnesses to transformations that unfold over billions of years, carrying their cargo of frozen atmospheres, subsurface oceans, and chemical memories across distances that dwarf human comprehension, while maintaining the patient indifference of objects governed by physics rather than intention. The galaxy itself evolves around these wandering worlds as stellar populations age. Heavy elements accumulate through successive generations of stellar nucleosynthesis, and the large-scale structure of dark matter continues its expansion-driven evolution toward configurations that will characterize the universe's far future. When star formation ceases and galaxies become islands of cooling stellar remnants, separated by voids that grow larger with each passing billion years. Rogue planets persist through this cosmic aging process as among the most durable objects in the universe, requiring no external energy sources to maintain their basic physical integrity, and carrying their internal heat sources through eras that exceed the main sequence lifetimes of all stellar types. The magnetic fields generated by convection in their metallic cores provide protection against cosmic radiation that operates independently of stellar proximity, creating magnetospheres that deflect charged particles and preserve atmospheric envelopes across cosmic timescales. These protective magnetic barriers allow rogue planets to maintain complex chemical environments and subsurface liquid water throughout their billion-year journeys between stellar encounters, creating oases of chemical complexity that persist in the near vacuum of interstellar space where temperatures approach absolute zero and molecular motion nearly ceases. During their travels, rogue planets serve as gravitational sculptures that subtly influence the trajectories of smaller objects they encounter, creating complex patterns of orbital modification that propagate through interstellar space like ripples in a cosmic pond. Each gravitational interaction redistributes kinetic energy and angular momentum among the participants, gradually reshaping the velocity distribution of objects throughout the galaxy, while preserving the total energy and momentum of the system, according to conservation laws that operate with mathematical precision across all scales of cosmic architecture. The chemical evolution recorded in rogue planet surfaces provides archives that preserve information about galactic conditions spanning billions of years of cosmic history. As these worlds encounter different regions of interstellar space, they accumulate dust and gas that reflect the elemental abundance patterns characteristic of different galactic environments, creating layered chemical records similar to ice cores that preserve terrestrial climate history, but operating on time scales that encompass entire epochs of stellar evolution and galactic rotation. Orbital resonances between rogue planets and their remaining satellite systems create mechanical energy sources that persist throughout their galactic journeys, driving tidal heating that maintains geological activity and subsurface ocean circulation across cosmic timescales. These gravitational interactions operate with the reliability of clockwork, converting orbital energy into thermal energy through friction and elastic deformation that provides renewable heating independent of external stellar radiation or radioactive decay processes. The possibility that complex chemistry or even biological processes might operate in rogue planet subsurface oceans transforms these wandering worlds from barren wastelands into potential biospheres that carry life across galactic distances through gravitational processes that operate on scales vastly larger than any individual stellar system. Such mobile ecosystems could serve as vectors for distributing biological innovations throughout the galaxy, creating evolutionary connections between stellar systems separated by thousands of light-years and timescales that exceed the duration of complex life on any individual planet. Future gravitational interactions with other stellar systems provide opportunities for rogue planets to experience temporary episodes of stellar heating that briefly activate surface chemistry and atmospheric dynamics before returning to the deep freeze of interstellar space. These thermal cycles create periodic opportunities for chemical evolution and potentially biological activity that operate on timescales determined by galactic orbital mechanics rather than the shorter cycles that characterize planetary systems bound to individual stars. The vast numbers of rogue planets wandering through galactic space suggest that they represent a significant fraction of the total planetary mass in the universe, potentially outnumbering gravitationally bound planets by ratios that approach 10-1. This invisible population of homeless worlds creates a previously unrecognized component of galactic structure that influences cosmic evolution through gravitational effects, chemical processing, and possibly biological activity operating in environments completely disconnected from stellar energy sources. Computer simulations of galactic evolution that include realistic populations of rogue planets reveal complex feedback mechanisms through which these wandering worlds influence star formation rates, heavy element distribution, and the efficiency of material exchange between different galactic regions. The gravitational effects of countless rogue planets create subtle perturbations in gas flow patterns that modify the conditions for stellar formation, while contributing to the mixing processes that homogenize chemical compositions across galactic distances. Some rogue planets will eventually escape the Milky Way entirely through gravitational interactions with massive objects or close encounters with the galactic center, beginning intergalactic journeys that will carry them across the cosmic voids that separate galaxy clusters. These ultimate wanderers will experience conditions where matter densities drop below 1 particle per cubic meter, and where the cosmic microwave background provides the only external energy source, creating environments more isolated than any found within galactic boundaries. The thermal evolution of rogue planets during their eternal journeys depends on internal energy sources that operate according to nuclear physics principles that remain constant throughout cosmic history. Radioactive decay will continue providing internal heating for timescales that exceed the current age of the universe, ensuring that some rogue planets will maintain subsurface liquid water and geological activity long after the last stars cease nuclear burning and the universe enters its final era of expansion and cooling. During the far future, when stellar formation ceases and galaxies become graveyards of white dwarf stars, neutron stars, and black holes, rogue planets will persist as among the last repositories of chemical complexity and potentially biological activity in a universe where most matter exists in the form of elementary particles, radiation, and exotic stellar remnants. These wandering worlds might serve as arcs that preserve records of planetary evolution and biological innovation across timescales that encompass the entire thermal death of the universe. The radio signals detected from mysterious sources in intergalactic space might originate from rogue planets equipped with natural or artificial mechanisms for generating electromagnetic emissions, creating beacons that operate across cosmic distances and timescales. Whether these signals represent natural physical processes or technological communications from civilizations that survived planetary ejection, they demonstrate that isolated worlds can maintain complex electromagnetic activity throughout their journeys between stellar systems and possibly between galaxies. Each rogue planet continues its solitary passage through the cosmic dark as a self-contained world, carrying whatever chemical complexity, geological activity, and possibly biological innovations it accumulated during its formation and early evolution. These wandering laboratories explore regions of the universe where no other complex objects venture, serving as ambassadors from the era of active stellar formation to whatever cosmic environments await in the universe's distant future when expansion, cooling, and entropy have transformed the cosmic landscape into configurations that current physics can predict, but human imagination struggles to comprehend. The signals fade into cosmic silence, their mechanical precision dissolving into the gentle randomness of thermal noise that fills all empty spaces between the stars. Radio telescopes turn toward other patches of sky, their data streams flowing into computers that process new mysteries with the same patient algorithms, seeking patterns in the electromagnetic symphony that plays continuously across frequencies spanning the entire observable universe. The repeating bursts become archived observations, catalogued alongside thousands of other unexplained phenomena that await theoretical understanding or technological capability sufficient for deeper investigation. In the vast darkness between galaxies, rogue planets continue their eternal drift through regions where matter exists in concentrations so low that individual atoms might travel for millions of years without encountering companions. These wandering worlds carry their histories written in crystalline structures, isotopic ratios, and chemical compositions that preserve records of stellar nucleosynthesis, planetary formation, and violent gravitational encounters that occurred when the universe was younger and stellar systems were still adjusting to the architectural patterns that would define galactic structure for billions of years. The subsurface oceans beneath their frozen surfaces maintain temperatures and pressures where liquid water persists through radioactive heating and tidal interactions, creating isolated environments where chemistry operates according to the same physical laws that govern terrestrial biochemistry, but under conditions of complete isolation from stellar energy sources. Whether these hidden seas support biological activity remains unknown, but their persistence across cosmic timescales provides havens where complex molecular processes continue operating throughout billion-year journeys between chance encounters with other gravitational systems. Time moves differently in these remote territories where gravitational fields from individual stars become negligible, and only the galaxy's large-scale structure provides directional influences on object motion. Rogue planets experience time as a sequence of nearly identical epochs, punctuated by rare gravitational interactions that briefly perturb their trajectories before returning them to the steady motion that carries them along invisible currents flowing through the cosmic deep according to equations that describe matter distribution and gravitational evolution across distances approaching the observable horizon. The radio signals that reveal their possible existence grow weaker with distance, as the inverse square law dilutes electromagnetic energy across expanding spheres of space, until even the most sensitive receivers can no longer distinguish artificial patterns from the background radiation that permeates all regions of the universe. But the signals continue propagating outward at light speed, carrying their precise timing and mysterious periodicity toward regions where other civilizations might detect them billions of years in the future, when the galaxy's rotation has carried all current stellar systems into completely different configurations. Sleep comes gently to the wandering worlds as internal heat sources gradually diminish through radioactive decay, and tidal interactions weaken through orbital evolution. But these cooling processes operate on time scales so vast that they remain nearly imperceptible across the remaining lifetime of stellar activity in the galaxy. The rogue planets settle into thermal equilibria that will persist throughout the universe's expansion toward maximum entropy. When temperature differences disappear and the cosmic microwave background approaches absolute zero in a future too distant for current cosmological models to describe with confidence, in this cosmic twilight, where signals fade and temperatures equilibrate, the wandering worlds find their most profound rest in the mathematical certainty of physical laws that continue operating regardless of whether any observers remain to measure their effects. Gravity, electromagnetic forces, and the nuclear interactions that power radioactive decay maintain their fundamental constants, while galaxies drift apart and stellar formation gradually ceases across a universe that grows larger, colder, and more sparsely populated with each passing epoch. The eternal journey continues in silence and darkness, carrying its passengers deeper into territories where space and time assume dimensions that exceed human comprehension, while operating according to principles that remain constant throughout all transformations of matter and energy. In this deep cosmic sleep, rogue planets discover the ultimate stillness that awaits all objects when motion becomes purely relative and temperature differences vanish into the uniform coldness of maximum entropy. Sleep well, wandering worlds, in your passage through the infinite dark.